All right. Well, our next major topic in the sensation and perception content here is a bit of a continuation on the ecological approach, though it is a touch different. But one way that we can try to connect it to the ecological approach that we just covered in the previous set of recordings is to think again about local flow, right? So again, local flow is the idea that you are stationary and something in the world is moving, and that's going to generate a pattern that we labeled as local optic flow. That is, a small localized part of your visual field is moving, not the entire visual field, which is global flow. And that's what happens during self motion, like when you're walking, right? And we spent some time talking about a lot of the global flow stuff, and we touched on a little bit of local flow, specifically about the looming effect, right? If something is coming at you, you can detect its time to contact using the tau variable. Although it is, of course, worth pointing out that the tau variable also applies to global flow as well. So if you are walking towards a doorway, there will be at a constant velocity. Again, we have to make that assumption of constant velocity. Then there will be a tau variable for the door, right? And it determines your time to contact until you hit the door. So one way or another, though, we have that. But we need to get into a little more detail here. And I think I might have said this at some point in the previous notes about texture gradients and flow gradients, right? So a texture gradient, if you recall, in the optic array specifies the surface slant. And the flow gradient and the optic flow field, and again, think about that picture of the bird flying over the plowed field, and there's going to be this flow gradient to the left and to the right. That specifies the depth layout of the world with regard to where the bird is, right? And that's a function of how fast things are moving, how fast the optic flow is. Things that are closer to you generate faster optic flow, and things that are further away generate slower optic flow. And that continues on continuously as a gradient, right? There's a consistent rate of change in the speed of the optic flow. And I think I might have added somewhere in there, I hope I did, that this is also true for local flow as well, because if the flow gradient specifies relative depth layout, then if we think about looking at an object in motion, some parts of the object will be closer to you, and some parts will be further from you, right? That only makes sense because objects have a three-dimensional shape for the most part. When we did the tau derivation, we kind of assumed that it was sort of like a two-dimensional surface facing you, right? But most realistic objects will have a three-dimensional shape. And that means there's going to be a part of the object that's kind of what we will call convex, and it sticks out, and therefore it's a little closer to you than the sides of the objects. In a previous video, I think I used my elephant sculpture as an example, so let's do it again. Let's pull it up here. Okay, so here we go. In this case, I'm going to tilt it just a little bit this way. The trunk and the tusks of the elephant are closer to the camera than the ears or the back side here, right? So that means that if it was in motion, such as now, then the closer parts of the object will generate faster optic flow compared to the further parts. And that flow gradient specifies the depth layout along the side of the elephant. But that depth layout is a function of its shape. And so this means that perceiving the local flow gradient across the surface of the object helps you perceive its shape. And perceiving its shape could turn out to be very useful for perceiving what it is, right? And this relates to object recognition. And one of the things that we need to think about, I'm going to go ahead and try to step forward here, is that the object recognition content covered in the textbook focused almost exclusively on perceiving shapes and objects in images, right? As if you were looking at a photograph and it's a two-dimensional outline of a thing that has a characteristic two-dimensional outline. And from there, the challenge was for the visual system to try to analyze that information in terms of the activity of the striate cortex in the occipital lobe of the brain, primary visual cortex, right? So the simple cells and complex cells and end-stop cells were all described as playing some sort of a role and extracting out boundaries and contour ownership of objects so that we can somehow recognize the shape and turn that into a recognition of what it is that we're seeing, right? But that was static object recognition. And whether we're looking at a photograph or whether we're just treating the retinal image as somehow equivalent to a photograph, and the job of the visual system is to extract two-dimensional patterns from that snapshot that the eye as camera is taking, that eliminates optic flow as a source of information about the object, right? Because when you're just treating the eye as a camera that takes pictures, and we have this single image that the eye has, a single retinal image that we somehow have to extract all of that complex visual information from. Again, just like when we talked about perceptual constancy before, the challenge to solve how the brain manages to recognize seems to be insurmountable, right? How in the world does the brain perform this seemingly miraculous task of extracting information from a single static snapshot of the retinal image, such as maybe the elephant here, and somehow recognize what three-dimensional shape that is? Now, my elephant example is a more complicated version of the doors that we had discussed when talking about perceptual constancy, right? If you just look at the door and your eye takes that snapshot and you have that fleeting retinal image, it's not going to be, in most cases, an actual rectangular shape in the retinal image. So that means that the visual system has to somehow find all of those edges and corners and end points of the door as an object. But then what it's going to find in terms of the actual visual data is still going to be that trapezoidal shape, and it still has to do something else at some higher level of visual processing to convert that into a recognition of that visual image as a rectangular door, right? And so what if we eliminate this idea, right? What if we remember when we talked about at the very end of the constancy notes, we talked about spatiotemporal patterns. And that means, of course, allowing in some movement and some change over time. And that is also then a central part of the ecological approach because of the importance of optic flow. Optic flow necessarily entails allowing for a change in visual information over time, right? How do things move and change over time? Whether it's global flow or local flow on the surface of an object, there's going to be some pattern of change over time. And so can this help us now solve the challenge, or at least address the challenge of object recognition, if we allow some temporal unfolding of spatial patterns so that we can have a spatiotemporal pattern here, right? So that means that we need to perceive an object, but we also need to perceive certain changes that the object is undergoing. And if you recall, when we talked about the constancy issues, I talked about certain kinds of transformations, such as rotation, right? And the idea there was that when a door swings open, it is rotating around a vertical axis. And if we only allow the visual system to see that at one point in time, like a little snapshot of the door, it's hard to imagine how the visual system can understand that it has detected a rotating object. But of course, if we allow the visual system to extract information over time, then perhaps what's happening is that the visual system is detecting two different things at the same time. One is an object that has a characteristic shape, a rectangular door, and two, this rectangular door is rotating, and that rotation causes a certain transformation to occur in the visual input, but that transformation of the visual input is specific not to the object shape, but rather specific to the object's transformation, namely the rotating part, right? And so the claim here now is that maybe what the visual system can do is separately perceive objects and events, or objects and changes, as I have written it here on the slide. That's what we're really going to get into here. Just some examples here. Objects, clearly, not much, can hopefully that's confusing there. Well, except on the bottom where I have got a couple of words with question marks there, because what is a stream, right? You're standing, you're walking in the woods, you come across the little stream, you see the water flowing, or a river even, and is that an object? How do we define the stream or a river? Is it defined by what it is as an object, or is it really defined by the change that's occurring, and therefore it is inherently an event? The water might be the object, and so the stream is the event. And the same goes for an ocean and the waves rolling in and so forth, right? Yeah, that's a difficult, almost semantic problem to address, but it is also a perceptual problem too. And I wanted to throw that out there. We're not going to dive into that much, right? But over here on the right, we have the kinds of changes or events. I mentioned the rotation is the second one down. A translation is a straight line, linear movement, right? So let's come back to my elephant here. Here it is rotating, right? Now it's translating, right? And I'm going to translate it in a different direction as well. And also I can translate it in 3 dimensions, right? So movement along a single axis is a translation. Rotation involves that completely different. And I think the perspective change that we were talking about, like looking at doors from different perspectives, is essentially a rotation, because when the door swings open, it rotates. And now, of course, you're looking at the door from a slightly different angle, right? On the other hand, if you take a step to the right or to the left, you have translated your point of observation in the world, and you are still also now looking at the door from a different perspective or a different angle. So what we can really see here is that our movements through the world result in the so-called perspective changes could be broken down into a set of rotations and translations of the point of observation. All right, as we walk around, we move in straight line paths, and that's a translation. But sometimes we walk in curved paths, or we turn in place or turn our head, and those kinds of things result in rotations of the visual field. We also I tended to focus on rigid objects in the past when talking about constancy, but some objects are non-rigid, and that means things can stretch and grow and flow like water, of course, the splashing and the flowing, the streams and the waves again, right? But of course, Play-Doh and stuff like that clearly is going to stretch and bend and so on and so forth. And human bodies, of course, bend, right? So that's something that's, certainly a part of the world, or things that are bendy and stretchy and so forth. And it's also important to think about time scales, because when we think about events, what we've been talking about are things that occur on the order of a few seconds, a moment or two, like a door that opens or watching my hand do something. But some events take a little longer of a time scale, like a change in someone's appearance as they age. Now, is that something that is perceived? Well, I would think so, right? But it's not something that's perceived in the immediate moment. It takes time, even long time frames sometimes. Well, let's move on. So I said, that we're going to try to treat this as a continuation of the ecological approach. But one thing I want to do is I do want to also give a moment to talk about how does the sensation-mediated approach. It's not as if the sensation-mediated approach completely ignores motion perception and change perception. There are theories that are proposed to explain how we perceive change if we only rely on visual sensations. And well, the answer here is what's known as the image comparison hypothesis. And again, it kind of goes back to this idea that this classical theory treats the eye somewhat like a digital camera that takes snapshots of the world, and instead of pixels, we have the photoreceptors, right? Which then feed into all of those other cells that are deeper into the brain. But that taking that retinal image and treating it as a snapshot of the world is again something that does not contain change or spatiotemporal patterns. It contains only a spatial pattern, right? A distribution of light intensities across the retina is all that's there in that spatial pattern of the retinal image. That information from the retinal image is then stored in the brain. And then a moment later, the retina and the eye keeps doing its job. So it brings in new information. So it now gathers essentially a second snapshot of the world. And now we have the possibility of taking into the brain two snapshots of the world and comparing them. And one thing that we might notice is that those two snapshots taken a few moments apart will not be identical with each other. Perhaps because in the moment between those two images, my head moved a little to one direction, right? And that means I changed my point of observation in the world a little bit. And that means things are going to be in a relatively slightly different location in the scene. And so now the job for the brain is to figure out, well, by comparing these two images, I can see that something has changed. Some objects are in different locations in the visual scene. Some things have gone out of view, something else maybe has come into view. So now that I'm comparing these two images, I'm trying to figure out what has changed, what could have happened to cause that particular change in the visual scene, right? So again, just like when we talked about the sensation-mediated view before, when dealing with a single retinal image, I had proposed that the question was really, what is happening in the world that could have caused this current sensory pattern? Now what we're going to do is we're going to say, what in the world could have caused this change in the sensory patterns between these two images? And so just imagine a situation like you can do this on your phone, right? Where you do that thing where you can have several different snapshots taken repeatedly very quickly, right? So you go ching, 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 and you got several pictures all taken in a row as you move your camera from left to right, right? And you're going to get something that's changing. And you can look at those 5 pictures, let's say, all side by side, and they're all different. And you think, well, what caused that, right? What could have caused that? Well, clearly you know because you took the pictures, right? But for the brain, it doesn't know, and it's going to have to figure out, well, what could have caused this change? And maybe, of course, the answer is that the brain can successfully infer that my head was moving, and that's what caused the change. Or maybe it wasn't, it was something else that was moving, and that's what caused the change, right? But that's the idea behind the image comparison hypothesis, is that from the sensation-mediated view, we don't really have optic flow. We just have two different static images that are different from each other. And we have to infer what might have caused the specific change between those two scenes. Bit of a challenge, perhaps, right? So now what I was suggesting, though, is that we're going to allow us to have spatiotemporal patterns, that we can perceive change in and of itself. We don't have to treat the eye as taking a series of static snapshots of the world. And this idea, as I laid it out, is that we're going to be able to perceive an object and the change that it is undergoing at the same time. But importantly, these two things are very much connected to each other, right? And this is what I mean by codependent, is that perceiving an object does not happen in the absence of also perceiving some sort of change over time. And likewise, the nature of what we're perceiving as a pattern of change over time is very much a function of the shape and structure and size of that object. So each one informs about, or I should say, the information about the object and the change are inherently interconnected with each other, right? So let's get into the question now well, question here is, can change be perceived? But I've already asserted that we're going to assume or hypothesize that it can be. But we need to talk about the information about change, right? And that's what we're really concerned about in this unit when I've been talking about the ecological approach. What is the information about something happening, right? So we've treated the optic array as a form of information, patterns in optic flow as a form of information. So is there information in the optic array or the optic flow field about how something could be changing over time, such as a door that is rotating? And so that provides us some information, perhaps with about it, the shape of that object, but also perhaps even the distance to the object and the size of the object. That one's trickier, perhaps, but let's keep on going here. What I have, this is an embedded video here, so let's watch it. So as you can see, it's called the kinetic depth effect. And this is what we see, right? So what are we looking at here? Well, when I pause the video here, you're seeing a two-dimensional shape, right? Just a black two-dimensional shape on a white background. And from this particular perspective, you can tell that it's a stegosaurus, but maybe here, if you hadn't seen it already, you might not know what this is. It just looks like a bunch of random blobby things, right? So it is hard to see what it is and what kind of object it might be and what its three-dimensional shape might be. But as soon as we start letting it rotate, we can see its three-dimensional shape, right? And in fact, it is essentially necessary for us to see the movement before, bonus prize for anyone who knows what that is. It is important for us to see the movement in order to recognize this at all, right? A single static image is really never sufficient to allow recognition. It is only through the movement and the change over time that the three-dimensional shape and structure of each object becomes recognizable. And so, of course, the idea is that we are not seeing objects non-rigidly deformed. We're seeing a rigid object, a tree, a Dalek, a Stegosaurus, or a Yoda, and whatever else was there, I forgot, rotating around a vertical axis, right? So that means that there is, in fact, some important thing happening here that connects object recognition with patterns of movement, right? Now, obviously, this kind of demonstration is a not necessarily an entirely natural one, but the idea is that in the real world, we are constantly walking around and moving, and this creates that kind of, maybe as we walk around an object, it might create that similar kind of rotational movement pattern that could specify a three-dimensional shape. See if I can get past all of this. Here's another example. This one's going to be a little bit blurry. Unless, of course, I'm going to cause everything to crash. Hopefully my PowerPoint does not crash on me here. This one might not play, sorry. But this typically should generate a random dot looking object that's rotating around a horizontal axis. If you download the PowerPoints and run it in slideshow mode, you can probably get this to happen as well. Oh, it's going to be another failure. Okay, so let's keep on going here. Let's get to this one. This one sort of replicates the basic effect from the previous two that didn't work. So let me run this one here. So once again, we just got a bunch of black and white square checkerboard things going on here, right? But the relative motions and the changes and the speeds of these motions create what ought to be a reasonably decent impression of a three-dimensional cylinder shape rotating around a vertical axis, right? And so again, the idea is that we can perceive three-dimensional shape. Here's another one. So now we have a sphere rotating around a horizontal axis. Bit more obvious and apparent, I think, that we are seeing that. Now notice as I move the mouse here, this object, the video is titled 3D Structure from Motion. So that's another way to talk about what I previously labeled the kinetic depth effect. So kinetic depth effect means that the depth becomes apparent once we allow this thing to start moving. It's kinetic, right? But here, a three-dimensional structure from motion is also an important word to use because of the idea that it is through the structure in the, or the way this thing moves that gives it a three-dimensional structure. And by three-dimensional structure, I mean it has a particular shape. We can clearly see that it is spherical once it is moving. Once I hit pause on the video, that spherical shape disappears. It just looks like a circular arrangement of dots with more of them clustered around the outside. It does not really look like a sphere until we let it go, right? Oh, this one's probably not going to work either, so let me skip on past that. I'll skip on past that one. Again, sorry for the ones that are not working very well. But again, I have the PowerPoints in the modules, so if you download the PowerPoints, those might work. I'll try to find the original files as well and upload those into the modules if the PowerPoints alone don't do the trick. Well, anyway, how do we explain the ability to get three-dimensional structure from motion? And here the answer is from the relative optical velocities. This is similar and related to motion parallax covered in the chapter on depth perception, right? The idea, again, just we talked about optic flow gradients, things that are further away move a little bit more slowly compared to things that are closer. And that's true on a ground plane as you drive down the road, but it's also true on any single object that you hold in your hand and examine, like my elephant here, right? So as I just turn the elephant around in front of the camera, there will be some motion parallax here, so that parts of the elephant that are closer to the camera will move faster than the parts that are further away. And through that movement, we generate three-dimensional structure just from the motion itself, giving us information about object shape and orientation, and maybe even size and distance, right? So now that we have that under our belt, this is where I want to stop the video for now. But I want to just kind of leave it with the point that there is potentially information available in motion, right? So the information about depth and distance in the world is one thing, but also information about shape of an object and therefore the identity of an object, right? And so information coming from motion, providing us with this three-dimensional object structure, can be a way to address the object recognition problem, right? That the patterns come from movement over, and again, the concept of a spatio-temporal pattern, information embedded in the way things move, is very central to the issue of event perception, which was a field essentially invented by this guy, Gunnar Johansson, in Uppsala University in Sweden back in the 1950s, who was working, actually had trained in the Gestalt tradition and was interested in the issue of object recognition, but noted, of course, that object recognition and event recognition might be intertwined with each other very crucially. And so I'm going to stop it here, and then we'll come back for part 2 and move on with Johansson's research.